Okay, great. So I'd like to talk today about something that I threatened to talk about last time, called the periodic table.
Oh, now people are complaining it's very quiet.
I'm not!
Could you put is the mic quite low down in your shirt?
Yeah,
Maybe put it further up? No, it's not that low.
it's not all that low. I could stick it in my mouth.
Okay, let's just see what people in Zoom land say.
Hey, folks in Zoom land, we have no ability to control the microphone?
We can't control the volume.
The volume.
Well, someone's saying they think it's fine.
I'll talk loud. I like talking loud. So the periodic table is a structure which organizes our concepts about n categories. So what's an n category? Well, I'm not going to say much about it, but I said last time that it's a thing that has a bunch of objects, and then if you have at least a one category, then you could have one morphisms or morphisms between objects. And if you have at least a two category, then you can have two morphisms going between one morphisms that start and that share a common source and a common target. And then if you have at least a three category, you can talk about three morphisms between two morphisms that have a common source and a common target, and so on. And you have a bunch of operations for how to compose these morphisms, which go up to level n, and then we stop if we're in an n category. There are infinity categories where you never stop, but I'll mainly be talking about n categories. There are lots of ways to compose these, and we can compose them in general via what you could call cell colonies. So what's that? So you take a non-empty list of objects, and then for each successive pair of them, you put in a non-empty list of one morphisms. So by list, I mean, of course, an ordered finite set, totally ordered finite set. And then for each, and you're allowed, and then between any two one morphisms that have the same source and target, you can put in a non-empty list of two morphisms. I'll put in three there. And so on up to level n. So maybe if I wanted a three category, if I was studying three categories, I would go up to here. I don't have to go up that high, but if I have more than one two morphism in my list, then I have to stick some three morphisms in between there. And so this is the kind of thing that you should be able to compose. You should be able to compose all these guys and get a three morphism in a three category. And this is just an example of this general pattern of a cell colony. And then there are a bunch of laws that hold, but all the laws hold only up to higher morphisms. And the way the laws work for composition is that sometimes when you have one of these cell colonies, you can interpret it in a number of ways. And for example, for this one, you could say that we're going to compose all three of these morphisms in one go. So that's the fundamental thing you do with a cell colony of that sort. But it has this sub-cell colony, and you could compose those two morphisms in that subcolony and then compose it with this one. Or for that matter, you could compose these two and then compose it with this one. And the idea is that those should all be, well, equal if you're in a one category, but then just have a morphism between all of those things if you're in a bi-category or tri-category or so on. So in a one category, we'd have this kind of associative law like this, but in a two category or higher, we would say no, we don't demand that those are equal, we just demand that there are two morphisms going back and forth between those. And if we were just in a bicategory, we would demand that these are inverses. But if we were in a higher n category, we would say, no, they just need to be inverses up to a higher morphism. And it proceeds on in an inductive way that gets rather tricky to describe in detail. But this cell colony here is sort of the fundamental, provides the most exciting law for a one category, or a category, namely the associative law. And it's a fundamentally one-dimensional law. It says if you line up a bunch of things, there are different ways to think about it, but they're all the same. Similarly, I mentioned last time in a fair amount of detail that this provides the fundamentally new law about bicategories, because this is something that can be interpreted in several ways. You could think of these composed and then these composed and then sticking them together, or you could think of these two composed and these two composed and then stick together like this, and so you get this. So in a bicategory, those would be required to be equal, and that's called the interchange law, just as this gave the associative law. In a tricategory, this interchange law would hold not as an equation, but up to isomorphism. Now, there's a lot to say about that, and it's sort of why n-category theory has been advancing somewhat slowly, is that it's rather a deep and tricky subject to work out all the details in a way that's convenient enough so that you can then go ahead and actually do things. But I instead want to talk about something else, which is assuming that we've got it all working. Notice this. So there's a concept of a monoid, which is a set with an associative product and unit. And there's a way that a monoid gives a category. And it gives a category with just one object. It's a sort of self-evident idea that if you have a monoid, so it's a set where you can multiply things, you can think of the elements of that set as morphisms from some object to itself. And multiplication in the monoid is composition of those morphisms. And so here the trick is that we're thinking of a monoid, which has elements, which is, right, a monoid is a set, so it has elements that you can multiply. And you're thinking of it as a special kind of category, where you're thinking of the category as having just one object, which was sort of not visible there, but the elements are becoming the morphisms in this category. So it's just a change of point of view. Yep?
Maybe I should have asked this the last time, but I was just going to ask, so I'm kind of used to the idea that various, when you're like that there's kind of some important example that motivates some abstract thing, like the integers motivate the definition of a ring or something like that. Is there something like that here to have?
Oh gosh, yeah. I mean, ask me to talk a year. Yeah. So any topological space gives you an n category for all n, where the objects are just the points in the space, the morphisms are the paths, the two morphisms are the paths of paths, and so on, right? So I just gave you lots of examples. And those examples are the examples where everything is reversible. If you have a path, you can go back the other way. So those are called n groupoids. So I just sort of told you what all the n groupoids in the world are, because we hope that that all of them come from spaces. But the ones, so in a sense, the sort of new stuff is ones where they aren't invertible, where you have higher morphisms or higher morphisms that aren't invertible. And there are many examples of those as well. But does that at least help for now? Okay.
By the way, you might want to repeat questions. I think the mic won't pick them up.
Oh, okay. So the question was like, can you give me an example of all this stuff? I'm stating it more tersely. Yeah.
Or maybe is there a simplest example to keep in mind? You're saying the case of a topological, any
That's a really big example. I mean, so there's the category. Here's another example which you're not going to like at all. Okay, so there's the category of all sets and functions between them. That you should like. Okay, that's why we got interested in categories. And then there's the two category of all categories. Now that you might not like so much, but there are categories, there are functors between categories and natural transformations between them. Then there's the three category of all two categories and so on. So this is like, if you liked n categories a lot, then you're gotta like n plus 1 categories. But that's one of these proofs by induction that doesn't work so well when you're trying to convince people to like things, right? So although you know, movies that have endless series, they sort of follow that inductive pattern. So I also gave you, if you like ever multiplying things or adding them, you like monoids, so you must like categories, even if you only like categories with just one object. So this pattern goes on, and it's the basis of the periodic table. So the pattern is that you can look at n categories that are boring on a bunch of bottom levels. So we say a k-tuply monoidal n category what is it? It's an n plus k category that's boring on the bottom n levels, that is with just one object, which I'll just call star, one morphism. What is it? Well, it has to be the identity morphism of star. Then one two-morphism, which is the identity of that. And so on up to just one, well, k minus 1 morphism. K minus 1 because we started counting it at objects, which are basically zero morphisms. So why do I call this a k-tuply monoidal n category? Well, it's because you can think of it as an n category. So the idea is we've got this one object, star, its identity, and so on up to just, so we just have one k minus 1, did I say k minus 1? Yeah, good, k minus 1 morphism. And then we get interesting stuff. So we get a bunch of k morphisms, perhaps. And then all the way on up to n plus k morphisms. Okay, so if we have such an n category, we can say forget about this boring bottom stuff, just like it did in the example of the monoid, or of the category with one object, and just think of it as an n category. So we just call these first interesting level, we call them the objects, and then one morphisms, two on, up to n morphisms. So it's really an n plus k category with this special property here, or structure actually, but we're thinking of it as a special kind of n category. Does that make sense? So why is it special? Well, one reason it's special is because the things that you're calling objects, what they really are is that they're kind of k morphisms all go, I mean, they have to start and end somewhere, therefore, so they start and end here. And so that means that you can compose them. So you're able to compose these objects, just like you were able to multiply elements of a monoid. But because there's extra bottom levels, there's like even more stuff that you can do. So it turns out that these k-tuply monoidal n categories are very interesting. So let's make a table of them. And that's the periodic table. It's not actually periodic, but it's like the periodic table of Mendeleev in that it lets you predict new elements, predict new things. So like Mendeleev predicted germanium, the chemical properties of germanium by looking at what came after, what came below silicon. So it works like that. So let's just do these three choices. And then let's look at k equals 0, k equals 1, k equals 2, k equals 3, and maybe some more. Okay, so what does 0-tuply monoidal mean? Well, that means, like, forget it. There's nothing down here. It's just a plain old n category. So a plain old 1 category is just called a category. This would be a 2 category, but technically, I mean a bicategory, tricategory, and, well, one has to learn lots of Greek to keep on going. What's a 0 category? It's just a set. All you've got are the things that which are objects, but we don't even call them objects. In that case, we just call them elements, right? So there we go. Those are the things we've got. Okay, now I already showed you that a 1-tuply monoidal category, a 1-tuply monoidal 0 category. What's that? That's really a category, but with just one object. So categories with just one object were monoids. And so the idea is that a monoid is a special sort of category. So whenever you have a monoid, you can reinterpret it as a category with one object. And that process sometimes goes by the name B. So there's actually a map from the thing of all monoids to the thing of all categories called B, or sometimes D-looping. And it goes on like this. So a bicategory with one object is called a monoidal category. So basically the idea is it's a category, but where you have the additional ability to compose objects now, because there are morphisms in the bicategory. So it's like a category where you can multiply objects. There are millions of these. So for example, in the category of sets, I can multiply sets. Well, I take the Cartesian product of sets. So the fact that sets have a Cartesian product means that it's a monoidal category. Or, for example, vector spaces. There are various ways to multiply vector spaces. I could take the Cartesian product, but let's just for fun, I could take the tensor product of vector spaces. That's a really classic monoidal category. And there are zillions of things like this. So most categories of mathematical gadgets have some kind of way that lets you multiply or glom together or add to objects. Maybe I should have also thrown in the fact that I could take sets and disjoint union of sets, which is called plus by show-offs. So that's also a monoidal category. So you can make the same category monoidal in multiple ways, just like you could take the same set and make it into a monoid in multiple ways. Okay, that's all I'll say about those, but those are bicategories with one object. And that pattern just keeps on going. So you've got monoidal bicategories. I'll give you some examples. If I have time, I'll give you examples of those. They're really exciting. But I want to get into the less obvious parts of this pattern here. And it comes in right now when we start looking at k equals 2. So in other words, we are looking at what are these things that are monoidal categories with just one object, or what they are bicategories with one object and one morphism. So what are these things? Well, I'll just tell you, and then we'll see why. They're commutative monoids. And this is where things start getting interesting. So there's the theorem, which I'm not really going to prove, but I will say some stuff about. So I'm saying that a bicategory with one object and one morphism, which has to be the identity, is a commutative monoid. And vice versa. I mean, meaning that you can reinterpret any commutative monoid as a bicategory of this sort.
I'm going to make an annoying comment.
Yeah. We're friends. That's why I get to. That's what you always want to say, right?
Let's include the word actually.
Okay, actually, yeah.
Actually, it's a commutative monoid with a distinguished invertible element. It's a weird thing.
Yep, that was annoying. We could discuss this ad nauseum or ad infinitum, whichever comes first. But I have a lot to say about that. So I will repress all of it because I think I'm right. And in my confidence, I will just ride roughshod over that remark. I think there's something wrong about what you said, even though it's true. Okay.
True but wrong.
Yeah.
Okay.
It's morally wrong. So, okay, but let's see what's going on here. So we have one object, one morphism, which is the identity, and then lots of two morphisms potentially going between those. So let's look at them. So like here is a way of composing those guys. These are all the identity here. So that's called A, B. Now, it turns out, that the identity two-morphism acts as the identity both for the vertical form of composition and also the horizontal form of composition. So I can rewrite this as A and then this identity, which is it's an identity two-morphism. And I can stick an identity here too. So I'm basically rewriting B as the identity horizontally composed with B, and similarly with A, but in the other order. So this would be, you would be denoted A. Well, last time I introduced notation where I wrote it like this, where I'm not writing all the decorations on the one now. That's what I wrote last time for the notation for the vertical composition is just juxtaposition. The horizontal composition I wrote with a circle. But now that we know that the bicategory with one object is a monoidal category, and I said that like we often call the multiplication of objects tensor product, I'm just going to use different notation and draw this as tensor product. It'll make some of you happier, I think. So now, but the interchange law said that we can also interpret this in the other way. A composed with one tensor, one composed with B. So now I'm using that law just to mildly reinterpret things. But then I can multiply this out, right? So this is A, and this is tensor B. And so if I draw that, it looks like this. So this is equal to A tensor B. So we've already learned that although there seem to be two ways of composing, namely the ordinary juxtaposition and the tensor product, in this example, where there's only one object and one morphism, they're actually equal to each other. And then we can keep on playing this type of trick. And so I'll play it. Oh, I'm almost out of space. So now I am going to start. I'm going to start doing something else. Yeah, I'm going to put the. Now I'm going to start moving the B up front. Yeah. I'm just writing 1 instead of 1 of star because it gets too tiring. So here you see I've just written A as a tensor 1, and I've written A as 1 composed with A, and then I'm tensoring that with B composed with 1. Yeah, so that's equal to that. Then I use the interchange law again to write it as 1 tensor. God damn, I can talk and write at the same time. 1 tensor B.
Is this tensor vertical or horizontal?
Tensor is horizontal. I was doing it okay.
Oh, yeah, right.
Yeah, it's okay. I hate this stuff. Okay. I mean, I hate having to talk and write and think about what I'm going to say next. Life is so complicated. So, A tensor 1. But then, 1 tensor B is just B, and A tensor 1 is just A. So this is just B composed with A. So what have we done? We've shown that AB is equal to BA, and also we've shown that the multiplication by juxtaposition is the same as the tensor product. So the tensor product is also commutative, right? So AB is the same thing as A tensor B, which is BA, and so of course that's also B tensor A. So you started out thinking you had 2 operations, and you discover you have 1 commutative operation. So that's why we get a commutative monoid. And you can go reverse and show that if you have any commutative monoid, you can cook up a bicategory of this form. So commutativity has been born. You may have wondered why the commutative law was so popular. This is actually why. And that sounds crazy at first, but if you look carefully at what just happened, what we did is we used this doubly monoidal structure, that is the presence of 2 dimensions, to move 2 things around each other. The basic reason for the commutative law being so popular is that if I have an eraser and a thing of chalk, I can prove that's the same thing as having a bunch of chalk and eraser just by moving them around each other. I would not have been able to do that if I was living in line land in 1 dimension. Then no one would have thought there should be any intuitive reason why those were the same things to have, because you couldn't turn one of them into the other. But if you have 2 dimensions or more, then you can move things around. And so that's why this is so cool. Now, it goes on like this. So it turns out that this argument that I gave, which is full of equations, is recapitulated in the next case, that is in a monoidal bicategory with just 1 object. But because this next case has higher morphisms, it has morphisms between these 2 morphisms. Well, maybe I should think of it this way, right? So in the next case, we'd be dealing with a monoidal bicategory with just 1 object, but you could think of that as a tricategory with 1 object and one morphism. So the pictures would look just like this, except there would be this new extra level on top of the 3 morphisms, which we didn't have here. And so this whole argument would be carried out the same way, except that these laws, instead of holding as equations, would become 3 morphisms. So we would get, sorry to do this to your notes, but I just can't bear to rewrite all that stuff. So instead of getting A B is equal to BA, we would just have a morphism between them. And it would be invertible because I could run the argument backward. So we'd get an isomorphism between AB and BA. Or what people usually would say is there's an isomorphism between A tensor B and B tensor A, which is also true. So there's this other theorem, which is that a tricategory with one object and one morphism is, well, people call it a braided monoidal category. And I won't give you the whole definition of that, but it's basic, roughly, for starters, it's a monoidal category with these isomorphisms called the braidings, B for braiding, from A tensor B to B tensor A for any pair of objects. Oh, when I say morphism, I mean one dash morphism. So if I have one morphism, I merely say one morphism. Did that actually help? That sounds very confusing. Yeah. So when you get started, you just talk about objects, morphisms. Then someone says, "Hey, there are two morphisms." Then, like when you're like super jaded, you say zero morphism, one morphism, two morphism, right? You would call an object a zero morphism, a morphism, a one morphism, and so on, because you say, like, we just got to number things systematically. But I'm sort of not up to that speed here. So this means, yeah, the kind of morphism between objects. So it's a tricategory where the bottom two levels are boring. Yep.
Does that mean something one level down in terms of monoids?
Well, it's got to, right? But yes. So here we have, well, but anyway, for right now, we have this braided monoidal categories in here. These wind up having to obey some laws, which you can derive from more fiddling around with these pictures. But the main point I'm trying to make here is that what we're seeing now is that this previous argument that said that, oh, you can move two things around each other, and so therefore A tensor B is equal to B tensor A. Now we say, no, they're not equal, they're just isomorphic, because we're actually keeping track of the process of moving them around. And so if I'm drawing the picture in a rather different style of three-dimensional picture now as a cube, which may be confusing. But the idea is that argument by which I move the A and B around each other, you can actually think of as the process of moving them around. And this is a little braid. This is people who started studying how braids are connected to algebra realized that braided monoidal categories are the way to relate the two. And so now we get like lots of invariants of knots and braids and such out of braided monoidal categories. But they're braided in this very literal sense that you have strands tangling around each other. So I will just rapidly say that there are such things as braided monoidal bicategories and braided monoidal tricategories, and so on. And the question was raised, the exciting question is what's over here at the k equals 3 level. So what's a braided monoidal category with just one object? Is it like something even more commutative than a commutative monoid? Well, it's hard to get more commutative when you're already commutative if you're just a set. So it turns out, interestingly, that you don't get anything new now. You get commutative monoids. Now Tom will argue, but I'm going to not listen to him. Not about that, anyway. So something really interesting happens here, which is, it's getting more complicated. And because I'm running out of time, I will just sketch some more of the chart. It is possible to get more commutative than a braided monoidal category. There's a thing that's very important called a symmetric monoidal category, which is what you get here. And so you see, at the k equals 2 level, although I was talking about algebra, I was talking about it with pictures, and so topology started sneaking in. My arguments began to resemble the manipulation of objects in space. And so when we had 2 extra dimensions, we were able to move objects around. But you see, at that level, at this braided monoidal category level, there were really 2 fundamentally different ways, at least 2 fundamentally different ways to move 2 objects around each other. So in a braided monoidal category, you actually have this morphism, BAB, which I'm drawing here, but there's also another morphism, which is BBA inverse, also going from A tensor B to B tensor A. So there are 2 different ways to braid things around each other. But that's when we have 2 extra dimensions, when k equals 2. When k equals 3, it turns out that these 2 ways become equal to each other. Because, well, see here I was drawing pictures in 3-dimensional space. And in 3-dimensional space, there's really a big difference between a knot or braid that has this and a knot that has this, right? But if I was in 4-dimensional space, which alas I'm not, I could move my arm, this arm up a little bit into the 4th dimension, just pretend, and then back down. And so we would get, at this level of the story, we would get that they're equal. So a symmetric monoidal category is a braided monoidal category where the braiding and this other inverse braiding are equal. So that's the sense in which symmetric monoidal categories are a little bit more commutative, oh, that's a funny thing to say, than braided ones. It's the 2 different ways of switching around things become equal. And by the way, over here, you still get commutative monoids. Now, I will just tell you that here, you still just get symmetric monoidal categories. So having further extra dimensions doesn't do anything for you. And if you've studied knot theory, you sort of know that like knot theory in 3 dimensions is really different than knot theory in 4 dimensions. Knot theory in 4 dimensions is boring because you can untie all knots. And knot theory in 5 dimensions is just as boring as it is in 4 dimensions, but no different really. And so what's happening here is an interesting pattern, which James Dolan and I noticed, although it had a lot of precursors, which is that it seems like the column stabilizes in this kind of manner. And in fact, it turned out, and I would love to talk more about this, but it turns out that here there are things called seleptic monoidal bicategories, which are not quite symmetric yet, but then if you go down to the next one, you get what are called symmetric monoidal bicategories, and from then on it does appear to stabilize. So this is called the stabilization hypothesis. That is, the idea of this pattern is called the stabilization hypothesis. And that's part of what makes this periodic table, well, not really periodic, in any exciting way. It makes it a useful organizing principle for understanding the wilderness of n categories. So how can we state this as a little bit more of a theorem or conjecture at least? Well, one way to do that is to notice that there are forgetful functors going up. That is, if I have a monoid, I can forget that I can multiply, and it's just think about its underlying set. If I have a commutative monoid, I can think of it as just being a monoid, and so on. So basically, we have these, U is for underlying, and that's a way that category theorists talk about forgetting stuff. And so the stabilization hypothesis, so Jim and I called it a hypothesis because it was even too vague to be a conjecture at that point, that the theory of n categories hadn't even worked out to the point where we could know exactly what we were talking about. But so the forgetful, well, it's worse than a functor. It's some kind of n functor, right? So there's a 2 category of categories. There's a 3 category of these, and so on. So it's something like a n plus 1 functor, I guess. U. So it's going from some thing of k-tuply monoidal n categories. So this is the n plus 1 category of k-tuply monoidal n categories. And, well, let me start at k plus 1. Okay. And then we're forgetting that it's k plus 1 tuply monoidal and just thinking of it as k-tuply monoidal. So it's going up the page there. So the hypothesis is that this thing is an equivalence if you go far enough down the column of the chart, which is if k, if I did it right, if k is greater than or equal to n plus 2. So like when n is 0, once you get up to k equals 2, the forgetful functor from triply monoidal to doubly monoidal is an equivalence. Yeah, I think I got the numbering all right. Our main reason for believing this was not that we just happened to see it in a pathetically small number of cases, but that there was a theory of stabilization in topology which has many manifestations, one of which was this knot theory idea, that if you're dealing with n-dimensional manifolds embedded in n plus k dimensional space, you can study a kind of higher dimensional version of knot theory. And when k gets big enough, that type of knot theory settles down and becomes very boring. So like one-dimensional knots, that is knots made of circles, is very interesting in 1 plus 2 dimensional space, but when you get up to 1 plus 3 dimensional space, then you can untangle them all. And that was known to hold for all these higher versions of knot theory. There's also a more homotopy theory outlook on this. There's something called the Freudenthal suspension theorem, which also involves this magic number here that made us convinced that it was working.
While we're on homotopy theory, can I
Yeah.
ask a question from Zoom?
Sure.
So someone asks, are k-tuply monoidal n categories the same as EK algebras in the appropriate category?
Yeah, that would, I mean, morally speaking, yes. So that there's a way to organize a structure that has k different multiplications that all get along with each other into what's called an EK algebra. It's an algebra of a certain operad. And so, so I should say that, like, while Batanin has given a nice definition of n category, he's given a proof of a stabilization hypothesis, which, as far as I know, does not really apply to k-tuply monoidal n categories as defined as I'm doing, saying that they're like have just one object, one morphism, blah, blah, blah. instead, he proves a version of the stabilization hypothesis for n categories that are algebras of an EK operad, and shows that when k gets big enough, then increasing k further doesn't change anything. So yeah, so very much so. I should probably stop, and this is probably a good time to do it. I'll just say that a really fun confirmation of these ideas, or I don't know if it's exactly a confirmation, but a fun piece of evidence for these ideas is to think about this stuff very carefully, and why there's yet this extra level in this column as compared to this column. And I guess I will just say a word about that. So for braided monoidal categories, right, you have that this is not equal to this. When you get to symmetric monoidal categories, you say, yeah, they're equal. But when you go up to the 2-category level, you say, no, you idiot, they're not equal. They're just isomorphic. There's just a process whereby you can get from here to here if there's enough extra dimensions of space. If you have enough extra dimensions that you can whoop your arm up into the 4th dimension a little bit and then slide it back down. But if you think about that carefully, there actually were 2 ways I could have done that. I could have moved my arm up a little bit into the 4th dimension and back down, or I could have moved it down in the 4th dimension and moved it back up. And those are really different processes, just like these 2 braidings were 2 different processes. So you get this process here called the solipsis. It's just a name. But there's also like another process, which is sort of some kind of upside down version of the solipsis. And they're really different. You cannot continuously morph between moving your arm up into the 4th dimension and moving it down into the 4th dimension. But if you had 5 dimensions, then you could. And so then you get symmetric monoidal bicategories where the 2 solipses become equal. Well, you say they're equal because you are just working in a 2-category and there are no 3 morphisms around. But then later on, when you wise up and start working with tri-categories, then you say, no, you idiot, they're not really equal. There's just a 3 morphism between them. And it keeps on going like that forever, you see. And so that's what generates this zigzag pattern, we believe. And so that's the kind of thing that convinced us, yes, this is probably going to work. Okay, I'll stop here and leave some time for questions, amazingly. Yes, yes.
There seems some essential asymmetry in category theory. You start off saying the objects need not be sets, but morphisms are sets. Does that mean that seems to imply that all your K2P monoidal n categories are actually small categories?
Just a reminder that the mic probably doesn't pick up the room.
So he was asking about the asymmetry in my definition of category, which I gave last time, where I said we have a collection of objects sort of weaseling around, and then for any pair of objects you have a set of morphisms between them. The main reason why I did that was not because I cared about size considerations, but just because when I categorified, I wanted to change that word set to category, and I didn't want to mess with the word collection because I didn't feel like it. So I mean, one answer to your question is, well, I should have said set all along, and then I should have replaced set with category everywhere, and then I would have gotten the definition of double category, and then I could march on down that road and talk about triple categories and so on, and people have studied those. But if you're really interested in the size issues, so then I guess you have a lot of things to think about. So you could, for example, make everything be set sized, or you could make, you could use Grothendieck universes to talk about different amounts of size, and you can have like, the biggest amount of size for your objects, and then like the next smaller amount of size for your morphisms, and so on. And I'm not really a super expert on the best way to organize those size issues within categories, but there is an interesting interplay between the size issues, and just the inherent structure of n categories, which, yeah, I think is people are still sorting out, I might say, yeah. In fact, they're arguing about it on Mastodon even today. They were, yeah, yeah. My friends were arguing with someone about it. Yeah.
What about double categories and all that stuff?
Well, I said there are triple categories and quadruple categories and so on, and people are starting to take those a bit more seriously. Marco Grandis has a nice book on n-tuple categories. He may have some other name for them, but
Is there a periodic table?
oh, is there a periodic table? I don't know. I mean, of course, you can always take those n-tuple categories and put enough restrictions on them so that they more or less boil down to these, right? So like squares, where the vertical edges are scrunched down to a point, are just bigons or globes. So you can think of a bi-category as a special kind of double category, and so on. So I mean, you can always do that. I'm not saying I know all the technical details of how you do it, but so in other words, you could phrase this same thing in the language of n-tuple categories. But if you wanted to like get some more interesting version of this hypothesis for n-tuple categories, I just don't know. Yeah, I just don't know if it is.
We're going to have to leave it there because there's someone else coming into the room.
Okay, sorry folks, we got to go.
See you next time.
Thanks.